All right, so as advertised, I will try and tell you a little something about radiatively driven winds, and in particular I'm going to focus on radiation pressure on dust grains. All right, so you can see the cast of collaborators there. All right, so I'll start with some basics, just some basics of radiation pressure, why it's interesting, some characteristic numbers you should keep in mind. I'll spend most of my time talking about a simple model system to understand radiation pressure driving, and then I'll end up with some implications and observational tests. All right, so this plot I, of course, don't need to put up here. Everyone knows the basic problem. Galaxy formation is too efficient if you don't put in feedback. So we know that even the most efficient halos convert no more than sort of a third of their baryons into stars. For other halos, it's far less. Something has to fix this problem, and the answer is feedback, where feedback is defined as magic. All right, so my goal is to try and demystify the magic. All right, so the question is, what terminates star formation? This worked better when he was actually the governor. Amusingly enough, this man's signature is on my PhD in physics. True statement. He was the governor of California when I graduated from Berkeley. A PhD in physics signed by Arnold Schwarzenegger is pretty good. A PhD in women's studies signed by Arnold Schwarzenegger, that'd be worth money on eBay. Yeah. All right, so what do we need? All right, so let's start by being idiots. Let's just do simple numbers. All right, if we want to suppress star formation, we want to turn off star formation and eject a significant amount of gas from galaxies, what is required? All right, well, let's suppose that I want to get to a mass loading factor of unity. That is, for every gram of matter I stick in a star, I want to take 1 gram of matter and throw it out of the galaxy. Well, I can phrase that in terms of momentum budget. All right, I can say, well, all right, for that 1 gram of matter that went into a star, I need enough momentum to raise another gram of matter to the escape speed from the galaxy. All right, so I can ask, how much momentum do I need per unit mass of stars formed? And that's this P over m thing. And of course, to have a mass loading factor of unity, I need that to be of order v escape. That is, I need, for every gram of matter I put into stars, I need enough momentum to launch 1 gram of matter to of order, say, 500 kilometers a second, or something like that, maybe even more. Depends on whether you want to get it just out of the disk of the galaxy into the halo, or if you actually want to get it out of the halo completely. All right, but I need hundreds of kilometers a second per unit mass of stars formed. All right, now, that's pretty straightforward. All right, now this is a lower limit, assuming that everything's perfectly efficient and that I perfectly channel that momentum into driving stuff at just the escape speed. If I'm somewhat inefficient, for example, I raise some of the material to 2 or 3 times the escape speed, or I raise some of the material to a speed that's less than the escape speed so it goes up and falls back, I of course need more. All right, now the fact that the star formation efficiency is less than 0.5 tells me that I need momentum per unit mass of order at least 1,000 kilometers a second in order to get anything interesting from the standpoint of regulating the formation of stars in galaxies, or at least getting baryons out of galaxies. All right, maybe 100 kilometers a second is sufficient to regulate star formation within galaxies by, say, blowing matter out of individual star clusters but not getting it out of the galaxy completely. And that's just because the escape speeds from star clusters are much, much smaller than the escape speeds from galaxies. All right, so escape speed is the key point. All right, now, what do I get from radiation? Well, this is the case where you do the advanced technique of calling up starburst 99 and running the damn problem. All right, and you can ask, well, how much momentum can I get out of just the stellar radiation field? This is very simple. All right, the momentum carried by a radiation field is L over C. You can ask, what's L over C per unit stellar mass? All right, so here's the luminosity, 2200 ergs per gram. All right, here's the total radiative energy that's integrated over time. So this is the instantaneous production rate. This is integrated over stellar lifetime to 100 megayears. All right, I get that many ergs per solar mass. You can phrase that in terms of c squared. All right, star formation is about a 10 to the minus 3 efficiency of the theoretical maximum. All right, and I just divide by c to get the momenta, and I get 200 kilometers a second if I use all of the stellar light. All right, so what that immediately tells me is radiation pressure is potentially important for individual clusters. 200 kilometers a second is a sort of interesting number. All right, but it's not important for launching galaxy scale winds or doing anything on galaxy scales unless I can find a way to get way more momentum out of the stellar radiation field than L over C. Now, how can I do that? How is that possible? Well, to answer that question, I have to tell you a little something about the energy versus momentum conserving limits. All right, now what we've been thinking about so far is the momentum conserving limit. So here's my cartoon. I've got my star, and now I've got some shell of dense interstellar material around it with some characteristic mass m and radius r. My stars inject momentum at some rate dp dt, and I just conserve momentum as I throw stellar photons into this shell of matter. All right, so I push the matter out, and I just conserve momentum. All right, and the shell radius is just set by momentum conservation. P dot times the time for which the star has been on is of order the mass of the shell times r dot. That's just momentum in equals momentum out. Now that's one way of thinking about things, but it's not the only way. The other potential way to think about things is I could say, well, suppose that instead of conserving momentum, I conserve energy instead. And those two aren't identical, and the reason is, all right, this is something you all did in a special relativity class at some point. Take two mirrors and bounce photons back and forth between them. Right? Every time the photon bounces, I get to extract a little bit more of its momentum. So the two mirrors will start to get pushed apart by the photon, and what I'm doing is I'm tapping into the energy of the photon. So every time the photon comes off, it's a little redder than before, and so I'm taking the energy out of the photon and putting it into kinetic energy. So I could have the energy conserving limit. All right, and so I say there's some energy injection rate, dE dt. So there's some radiation field that's trapped inside here, bouncing back and forth. All right, in this case, the photons aren't reflecting off mirrors. It's infrared radiation that's trapped by dust grains, but it's the same basic idea. All right, and so I say energy is conserved. All right, and I say energy in, E dot times T, equals the kinetic energy of the shell plus however much energy there is in the interior, which is of the same order of magnitude. All right, so that's the energy conserving limit versus the momentum conserving limit. Now, what's the difference between the two? Well, all right, let's consider a source with some luminosity L, and after time t, the shell has some mass and radius r. This is the energy conserving case I wrote down. This is the momentum conserving case. And I can just ask, all right, so at a given time or radius or whatever, what's the ratio of energies and momentum between the two? And let's focus on this. This is the ratio of momentum if I conserve energy, the momentum the shell will have, to the momentum if I conserve momentum. All right, and you see that this ratio, square root MEC squared over LT, so this is the rest energy of the ejected material, the rest energy of the material that was launched off the stars, all right, versus the total luminosity. All right, if I compare the ratio of the energies, the ratio is C over the velocity of the shell. All right, so just looking at this, so if I look at a star-forming region that's, say, having a shell blown off it, all right, so I look at, say, 30 Dorados. I'll show you a picture of it later, being blown apart probably by radiation pressure. There's a shell of material moving out at tens of kilometers a second. The amount of energy I expect the shell to have at a given radius, if I conserved momentum, is smaller than if I conserved energy by a factor of c over tens of kilometers a second. That is not a small factor. Makes a huge difference. All right, so I can define the trapping factor. The trapping factor is the actual momentum that's in my shell of material moving outward divided by the momentum I put into it. All right, and I've taken away this 1, i.e., so it's P shell divided by P input. All right, so the question is, what's this trapping factor? Is it of order unity or is it very large? In order for radiation pressure to be a significant feedback on galactic scales, it would need to be very large. It would need to be at least of order 10. All right, so the question is it? All right, so hypothesis 1 is that the radiation field will effectively get trapped. That is, photons will get trapped inside this shell of expanding material, so F trap will be of order the optical depth of the shell, and that could be large. Hypothesis 2 is that, well, it may work for perfect spherical mirrors or perfect spherical shells of mass, but the ISM is really messy. There are always going to be holes. Stuff will leak out efficiently, and so F trap will be of order unity. So we want to test this. Yes?
So you also have some energy loss by heating, say, the dust grain. That will not affect this?
Oh, no. So there's certainly, so the energy conserving limit is truly extreme. Reality is certainly not going to be perfectly energy conserving, and for reasons like the one you just said. All right, so it's not, so think of those as the two extreme cartoons. If we're really energy conserving, all right, if I really took all of the stellar energy and put it into kinetic motion, I could eject every single baryon from the galaxy very easily. All right, so the question isn't, am I really in the energy conserving limit? It's just, can I venture part way into it such that I can extract 10L over C? All right, so let's try and, all right, so I have a confession to make. I don't do galaxy simulations. All right, cosmology is frightening to me. Galaxies, they're too complicated. I'm going to do something dumb and simple. I'm going to come up with a cartoon, because cartoons I can understand. All right, so here's my cartoon. All right, I've got a cloud of matter. Gravity points down. Radiation goes up. What happens? All right, so I'm going to consider some slab of material with a specified column density. I'll put it in the upper half plane at z bigger than 0, and I'll inject energy in the form of radiation at z equals 0 upward. There's a constant gravity force downward. All right, I'll say the opacity of this material looks like a dust opacity, so the Rosslin mean opacity goes like temperature squared. All right, and then I ask, what happens? All right, so I can now non-dimensionalize these equations, and I will spare you the god-awful algebra. If you really want, you can read this slide, but that would make you a huge nerd. All right, the point is, when you do this, there are two important dimensionless numbers that describe this system. All right, one is this quantity Fe star, and that's defined as what's the ratio of radiation force to gravitational force measured at the dust photosphere, and that's an important point. All right, because the opacity depends on temperature, the radiation force per unit mass varies depending on where you are. At the base of this column of material, where the temperature is high, the opacity is high, and the Eddington ratio is high. As I go up, the opacity is lower, the Eddington ratio is lower. So I have to, when I tell you about the Eddington ratio, always be careful to specify where I'm measuring it. And just for convenience, I'm going to measure it at the top of the atmosphere. All right, that's purely a convenience choice. It's not going to affect the answer, it's just I have to pick somewhere. All right, and similarly, there's this quantity tau star, and that's the optical depth. And again, I have to specify where I'm measuring it because the opacity depends on where I am. And simply by convention, I'm going to measure it at the dust photosphere. That's T star is the characteristic temperature of the dust photosphere. All right, and an important point to make is that this number is therefore much less than tau IR. The tau IR you frequently hear about is measured using the temperature and the opacity deep in the slab of material, where the opacity is much, much higher. All right, so just keep in mind, tau star is much less than tau IR. Part of the reason I like tau star better than tau IR is this I actually know how to calculate. Tau IR is a lot sketchier. All right. So let's ask, what happens? So first of all, I can ask, is there a hydrostatic solution just for this atmosphere? Can I find a hydrostatic solution? And the answer is yes. If Fe star is less than some critical value, I can find a hydrostatic solution and where radiation pressure just supports an isothermal atmosphere. All right? And this critical value depends on the optical depth. If the optical depth is low, I can find a hydrostatic solution at an Eddington ratio of nearly 1. If the optical depth is higher, the critical Eddington ratio goes down. All right, and it turns out that ultraluminous infrared galaxies and massive star clusters can live above this limit. They can live up here. All right, so then I ask, well, what about the unstable regime? What happens if I go above that line? There's no longer a hydrostatic atmosphere. All right, so here are some simulations I did with Todd Thompson. These are radiation hydrodynamic simulations. So we're solving the actual equations of radiation hydrodynamics here. All right, and the three columns I'm going to show you are tau star of 3, 10, and 10, and Fe star of 0.5, 0.25, and 0.5. All right, so initially all the matter is at the bottom of the box, and then I turn on the simulation and see what happens. Stuff starts to go up, but it immediately goes unstable and starts falling back. All right, and in the end, I don't wind up launching winds. Now the important thing to notice is, all right, if the amount of momentum I was getting was tau IR times Fe star, so this is tau star of 3 or 10, tau IR here is hundreds. All right, so if the multiplicative factor were tau IR, I should have been hugely super Eddington. I should have blasted this matter out and it would have been gone instantly. And that's not what happened. Instead, what happens is the material seems to self-adjust so that the mean Eddington ratio is always about 1. I'm left, thank you. All right, so the radiation drives the gas into this supersonically turbulent state where it self-adjusts to give you an Eddington ratio of about 1 without launching a wind. So F trap is vastly less than tau IR by like factors of hundreds. All right, and the reason this happens is because the radiation flux anti-correlates with the density. So here's a density map, just a snapshot from one of these simulations. And here is the radiation flux map. And what's happening is the radiation is leaking out the holes. The radiation is taking the path of least resistance. And this is missed in simple 1D models. Now, I should note there are some potential numerical concerns with these simulations. I'm using an approximation called flux-limited diffusion, and this is probably somewhat overestimated. Nonetheless, even if I'm off by a factor of 2, that means that tau IR is overestimated in a simple 1D model, not by a factor of, say, 500, only by a factor of 200. Still a problem. All right, now, you can say, well, suppose I crank up the radiation field even more relative to gravity. Can I launch a wind? And the answer is yes. Now let's go to FE star is very large. And you'll see I do launch a wind. These little zoom-in boxes are actually following. So what's going on in this movie, I'll show you again, is, all right, here is a zoom-in on the matter. And these boxes are actually showing the full simulation domain. And you'll see they move up as the calculation proceeds, and they just follow the matter. So you can see there is this turbulent matter, but it does get launched into a wind. And I can measure at what rate is momentum entrained into this wind. That is, I can directly measure F trap in these simulations. All right, because I know at what rate I put momentum in the radiation field, and I can measure the momentum of the matter as a function of time. And that ratio is just F trap. And here's the answer. F trap in these simulations can be bigger than unity. But to get up to 10, an F trap of 10, I need tau star of about 30. All right. That is an optical depth of 30 at the dusk photosphere. This corresponds to a column density of about 30 grams per square centimeter. All right, in solar masses per square parsec, that's like 10 to the 4 or 10 to the 5. That's what's required even to get to an F trap of 10. All right, so I can actually identify 3 regimes. All right, so let's just focus on this top panel, which is showing F trap. All right, so here I'm showing on the x-axis FE star, and on the y-axis tau star. All right, and if FE star and tau star are small enough, then I'm back in that stable case I showed you before where there's no instability. All right, if FE star is less than 1, all right, but tau star is bigger than 1, then I don't get a wind, but I do get this supersonic turbulence driven by radiation pressure. And if FE star is bigger than 1, then I do get a wind. All right, but F trap is relatively modest. It's never huge. All right, and in fact, you can write down a formula that just interpolates between the simulation data points and gives you the answer, and we put it in our paper. So if you want to implement radiation pressure as a subgrid model in your simulation, you should use our formula from this paper. All right, so what does this imply? What are the implications? Well, OK, so I've given you the 2-dimensionless numbers. You can calculate them for your simulations. You can also calculate them for real life. What are these 2-dimensionless numbers for actually existing astrophysical objects? All right, there are 2 cases we considered. One is young star clusters, and a second is galactic disks. All right, so for young star clusters, and the reason, incidentally, that things are a little different between these 2 cases is here you have a stellar population that has reached equilibrium between star formation and stellar death, and here you don't. The point to take away is that these numbers are never more than unity. All right, the highest you'll ever get is of order unity. And so what you should conclude from this is that F trap is basically 0. There's no radiative trapping. You just get the direct radiation pressure force. So your conclusion is radiation pressure cannot be the thing that drives galactic winds. All right, now, it can be important. Trapped radiation pressure is unimportant for star clusters, but direct radiation pressure can be significant because the escape speed is small. All right, and I will end with just a demonstration that that is in fact the case. So here's some observations by Lopez et al. All right, this is the 30 Doradus H2 region, and this is a map in 8 micron H alpha and X-ray. And from these, and if you're interested in details, you can ask me how, you can actually estimate the various sources of pressure inside this thing. All right, and you see that in the center of this thing, direct radiation pressure is in fact actually the dominant pressure that's blowing up 30 Doradus. So direct radiation pressure can be significant on the size scale of star clusters. It cannot be significant on the size scale of galaxies. All right, and that's where I'll end.
So I have a comment and a question.
I figured you would.
Yeah. So the comment is, even if you only have tau of 1 or 2, or F trap of 0 to 1, say, I disagree with the direct component not being important on galactic scales, because while I agree that probably means you won't launch completely out of the disk, out of, to unbind, you're still 200 kilometers a second is a sizable fountain, and B, if you're already in the halo, it can be above the escape velocity.
Sure.
It can't be important for accelerating material that's already.
Totally buy that. If you've gotten it out to the point where the escape speed is less than 100 kilometers or 200 kilometers a second, by some other mechanism, you can give it the last little oomph by radiation. Totally fine.
So the other question I was going to ask you, which you probably expected was coming, was what do you think will change, including the direct component in these calculations?
Right, well, okay, so we very carefully did calculations in the regime where the direct component is uninteresting. So I think maybe the question, are you asking about like Shane Davis's stuff? And okay, so that's not including the direct component, that's including a better approximation for radiative transfer than flux-limited diffusion. So I've seen some of Shane's preliminary work using this technique called variable Eddington tensor. All right, and I've seen some of the earlier work they published. Okay, so what I can say is, you certainly still get radiation Rayleigh-Taylor instability, and that certainly still does limit the rate at which you can transfer momentum to the gas. You get less radiation, you get less flux density anti-correlation than we get. So I suspect, to go back to this diagram of sort of F-trap versus these parameters, what's going to happen is this line is going to shift to the left. All right, so you'll be able to launch winds at FE star less than unity. You'll be able to launch them at FE star of sort of 0.5 or something like that. All right, probably the values of F-trap here will go up somewhat. All right, I'd guess based on just what I've seen in their simulations, it's going to be a factor of maybe a couple difference. So, but we'll see when they finally get around to publishing.
Question? Yeah, that's one. So just talk about the magnetic field. If they are tangled by, the gas are tangled by magnetic field, and then will that change the result?
So that's a good question. So depends on how strong the magnetic field is and what its geometry is. All right. So the basic answer is I think magnetic fields here are probably unlikely to be a huge effect, and the reason is in order to entrain material using the magnetic field, you need to be moving things at a speed that's not huge compared to the alphane speed, right? Magnetic fields are only strong when compared to motions where the speed is sort of comparable to the alphane speed. And if you're trying to launch galactic winds, you're talking about moving stuff at hundreds of kilometers a second. The alphane speed in the ISM is never, ever that high. All right, so I think the magnetic fields just aren't strong enough here to do anything interesting. Maybe on the cluster scales where you're talking about moving things at tens of kilometers a second, then they probably are interesting. But on the galactic scale, they're not. They're just not strong enough. Tom, do you want to comment on that?
One thing you might want to think about, though, is that all the long field lines that you have, they will connect to the small constant you have. So if you have some bubbles that you really drive out at high speeds, then it's their momentum ratio that can actually couple to the base of it. So I wouldn't quite dismiss it just based on the alphane speed.
Right, but it's hard to. I mean, those field lines can be, if I pull them at many times the alphane speed, they'll just bend and stretch, right? They won't transfer much momentum.
Yeah, well, actually, no, but you can actually drag and hold powder long. It's the opposite of magnetic draping.
Sure, but you can move it at speeds of order. You can't move it at 100 V alphane, right?
Right, you get the momentum ratio, right? So it's
right, okay.
low mass, high velocity on top.
Yeah.
You have high mass,
Right.
some lower velocity.
Okay.
So what happens if you had supernovae in your molecular cloud? Would they explode in a milieu that has been, whose density is going to be much lower because the radiation pressure has?
No, as I said, on cluster scales, I think radiation pressure clearly can push stuff away, right? I mean, if you look at a molecular,
And then it would boost the feedback from supernovae.
Absolutely.
It would not radiate.
Yeah, absolutely. If you look at molecular clouds in Milky Way like galaxies, they have escape speeds below 10 kilometers a second, and radiation pressure is probably not important for them. They probably get blown away just by the pressure of photoionized gas. If you go up to things with like 30 Doradus with escape speeds of of tens of kilometers a second, then I think radiation pressure does dominate, right? I mean, direct radiation pressure is important if the escape speed is measured in 10 or tens of kilometers a second. It's not important if it's measured in hundreds of kilometers a second.